let's start with 4.1. That's the exponential function. We started that in the class a little bit. Let's do it in detail now. How do you evaluate the exponential function, and what do they look like? They are defined like this: f of x equal a to x. Now this a has to be greater than 0, that means it has to be positive. A is not equal 1, and this x can be any real number, negative or positive, rational or irrational. It can be any real number. And we'll see why this a is greater than 0, why is that condition here in the later slides. Using the calculator, can we evaluate this? Yes, and this is how we enter it. To the caret sign, that's for the exponent, 2 raised to 1.4. You calculate that, and similarly you can calculate all of these numbers. And there you go, they converge to approximately 2.6651 and so on. These are the laws of the exponents. If you have the same base and you're multiplying them, you add the exponent. That's the product rule of exponent. This is a 2s to t. So you have exponent over the exponent. In this case, you multiply the exponents. Base is still the same. If you have product of two numbers and then you are raising it to exponent, now when this is a product, then you can distribute this exponent over these two factors, a to s times b to s. But if you have a plus b and then this whole thing to s, you cannot distribute the exponent over those terms, but you can distribute the exponent over the factors. 1 raised to any exponent is 1. A to negative s, negative sign in the exponent flips the number. The numerator will become the denominator. If it is already in the denominator, it will go to the numerator. But for this example, the negative, it flips the number and the exponent becomes the positive. After you flip the number, the exponent becomes positive. Any number raised to 0 equals 1. Why so? If you can bring that to the class, fantastic. Show it to me tomorrow. Let's see how the graph of exponential functions look like. Let's take an example of fx equal to 2x. You can create the table using your graphing calculator. You don't really have to calculate everything. By hand, you can use the table feature, table set of that, of the graphing calculator. You get all these values. When you plot that, your graph will look like this. You see that? It is increasing function. It is continuous. Here, as x approaches 0, the function value gets closer and closer to 0, but it never touches 0, because no matter what this x is, this value will never be 0. It will get as close to 0, but never be 0. So this what it looks like. This is the y-intercept 0, 1 for this basic function 0, 1. Any exponential function of the form a number raised to x will have this y-intercept, unless there are some graph transformations in it. Then this point, when x is 1, a is 2, when x is negative 1, y is half. So function value, this function value is same as the y coordinate of that. So this is the basic parent function of 2x. So these are the properties of exponential functions. The domain is all real numbers because it is extending on the positive side of x-axis as well as towards negative side of x-axis. There are no x-intercept. You see that y equals 0, that's the x-axis, that's the asymptote, the horizontal asymptote. There is no vertical asymptote. Y-intercept is this point 0, 1. When a is positive, a is greater than 1, this is an increasing function, and x towards negative infinity, that's your horizontal asymptote. This graph will always have these 3 points, 0, 1, 1a, and negative 1, 1 over a. These 3 points will always be on the graph of a to x. It is a smooth and continuous graph with no corners or gaps. So let's see how the graph of this looks like. Now I made that a less than 1. It is still positive, but less than 1. So this is the table we will get. And now when you draw that, this is the graph that looks like. So this is the graph of half to x. And now if we compare the graph of the previous function and this, that's what happened. So this is the graph of 2 to x, and this is the graph of half of x. Now half is same as 2 to negative x. This tells you the transformation of in the graph, that's reflection over the y-axis. So if this is a proper fraction, then you will have a decreasing function. X towards positive infinity will be your horizontal asymptote. The y-intercept does not change, still no x-intercept. Domain is still positive, negative infinity to positive infinity. Range is 0 to infinity. 0 is not included. In this case, this is increasing function. Domain and range is still the same for these two, both of them. But when this a is more than 1, it's increasing function. When a is between 0 and 1, this is a decreasing function. Now if you compare these two graphs, 3 to x and 1/3 to x, or 6 to x and 1/6 of x, they y1 and y2, in both the cases they are reflection of each other in the y-axis. This is 1/3 of x, this is 1/6 of x. When you plot that in the same coordinate y2, you will see the reflection over the y-axis. So these are the properties of exponential functions. When a is between 0 and 1, that means it's a proper fraction. It's positive, it is still positive, but it is less than 1. Domain is all real numbers, range is set of positive real numbers. No x-intercept, y-intercept is still 0, 1. The x-axis, y equals 0, is a horizontal asymptote as x extends towards infinity. This is decreasing function and it is 1 to 1. And remember, all the exponential function a to x, when a is a proper fraction, or if a is greater than 1, they both are 1 to 1 function. So this is the function of a to x when a is between 0 and 1. So let's compare them again. For these, the domains are same, ranges are same, y-intercept is same. This is increasing when a is greater than 1. Graph will be decreasing when a, oh, I made a mistake here. Okay, now a to negative x. So yes, in this case, when a is less than 1, decreasing on negative infinity to infinity. Now, let's see how this graph will look like. Let's try to graph this 2 to negative x minus 3 and determine the domain, range, and horizontal asymptote of f. So first thing first, what transformations are happening? First is reflection over y-axis. and then shift down 3, vertical shift down 3 points. So the parent function looks like this. The graph of 2 to negative x looks like this because it's a reflection in the over the y-axis, and then finally it shifts 3 down. Now the domain is still the same, negative infinity to positive infinity. Range is y greater than negative 3. The range is all real numbers more than negative 3. Horizontal asymptote is y to negative 3. So this is your horizontal asymptote as x extends towards infinity. The number e, that is extensively used in lots of exponential and log problems. So for many applications, that it's an irrational number, this e, which is equal to 2.718281828 and so on. It keeps going on. It's an irrational number. That means this decimal, there is no repeating pattern to it, and it's non-ending. This is called the natural base, and the function this is called the natural exponential function. If we try to graph this, this is the graph that looks like for e to x. Again, see the same thing. 0, 1 is the y-intercept. This is 1 point. This is another. These 3 points. So if you are plotting the graph of any exponential function, show me these 3 important points. Show me the horizontal asymptote. If there is any vertical asymptote or x-intercepts, show me all those things and draw the rough graph. You can copy that from calculator, that's fine. Let's see this one, negative e to x minus 3, and determine the domain and range and horizontal asymptote of f. So first thing first, because this is x minus 3, so horizontal shift to right 3, and then it is reflected over x. So this is the parent function, and that's what's happening after the transformation. Shift right 3 units and reflection over the x-axis. The domain is still same, negative to positive infinity. Range is negative infinity to 0. Horizontal asymptote is still that y equals 0 as x approaches negative infinity. Now we are trying to solve the exponential functions. Remember this formula that if a to u equals a to v, if the same base raised to some exponent are equal, that means the exponents are equal. So let's use that and let's see if we can figure that out. 2 to 3x minus 1 equal 32. So that means we can rewrite that 32 as 2 to 5th. Solve that. That means the exponents are equal. 3x minus 1 equal 5. X equal 2. That's the answer. Okay, next example is e to 2x minus 1 equal 1 over e to 3x times e to negative x raised to 4. Now, in this, first thing, you simplify this right hand side, which will be like this. This is the exponent over the exponent, the power rule, so this becomes e to negative 4x over e to 3x. If you combine this, now this is the quotient rule. So negative 4x minus 3x is e to negative 7x. So e to 2x minus 1 equal e to negative 7x. Bases are same, so 2x minus 1 has to be equal to negative 7x. And when you solve it, you get x to 1 over 9. Rest of the examples let's do later.